Okay, in this AC training, so far we have seen about architectural package, then the codes and standards, okay, then HAP calculation uh, for the various rooms, like then fresh air calculation, okay, then generator ventilation we have seen, okay. Today we will talk about transformer ventilation, right? If you go to one of the room layout, last week I have explained during the generator, okay, normally the power comes from authority, okay, it goes to the HV room, then from the HV room it will go to the LV room via transformer, right? So that is basically by means of authority, okay. Then from the LV room the power will be distributed to the SMDB, MDB, or you can say DB level, okay, inside your building the power will be distributed, right? Okay, now during the power failure scenario, what will happen? The power will not come from HV to transformer to the LV. What will happen? It will come from the generator. Okay, so the generator will give the power to the LV, then from the LV it will distribute to the internal. Okay, so whenever the equipment it works, okay, it will dissipate lot of heat because there is energy consumption, right? So whenever the power, the power transmission, okay, so it works. So basically when the mechanical equipment it works, it will produce it will have a efficiency, okay. So say for example like you can say like 95% or 96% efficiency, that means the 4% will be losses, right? So that loss is nothing but heat loss, okay. So that heat will be dissipated inside the room, so that unwanted heat to be removed from the space so that the equipment can perform properly, right? So the same method applicable for the transformer as well. Okay, transformer, what will happen? The power is transmitting from HV to LV through the transformer. Okay, because it is going to step down. Yeah. Sorry, there is some disturbance. Selva.
Selva, can you mute the mic, please?
Yeah. Selva or somebody, Jeffrey. Okay. See, now the same thing that the power comes from HV to the LV via transformer. Okay. So during the power transmission, the transformer works. Okay. So it can work, say for example, there is some efficiency, right? So that 95% or 98% there is some efficiency. The balance will be the heat losses. That heat losses means the heat dissipation from the transformer. So that will be dissipated inside the room. What will happen after some time? The high temperature will affect your temperature, your transformer efficiency. Then it cannot perform. It may say for example, instead of 400 voltage, it will go down to 390 and 380. Some point of time, the transformer cannot transmit the power. Okay, so that is the reason. That is the reason we are going to have a proper ventilation. Okay, I have one transformer presentation. Okay, small lectures for the transformer ventilation. So if you talk about as a concept, okay, so this is the transformer losses. Basically you have a core losses, iron losses, and then you have a winding losses, okay, in the transformer, right? So okay, say for example there are constant losses that occur regardless of the load on the transformer or due to the alternating magnetic field within the transformer core. Okay, so they typically occur due to hysteresis and eddy current in the core material. Okay, so basically we have two losses. One is the iron losses and another one is the winding losses. There are losses or load dependent, as they vary with the square of the load. The copper losses are result of resistance in the transformer winding. The losses are provided in the transformer's nameplate data or from the technical specification. So you can get the losses directly from the catalog itself. Okay, so the total loss is nothing but core losses plus copper loss, right? So this is the way you calculate the losses, how much losses it is. Okay, then this is the conversion. Okay, say for example if you want to convert from BTU per hour to kilowatt or watts to something, you can convert. This is just converting values from the heat dissipation, right? Okay, now remember we have seen last week or 2 weeks back the equation for the sensible load, then for the latent load and for the total load, right? Okay, now the transformer is a equipment. Okay, it is not a it's not a equipment that produces moisture, right? It is a sensible equipment, purely sensible equipment. So what is the equation to calculate your flow rate? CFM is nothing but heat dissipation divided by 1.08 multiplied by delta T, right? So normally we have equation called BTU per hour is nothing but equal CFM or 1.08 multiplied by CFM multiplied by delta T, right? So this is the equation to calculate your sensible load. Okay, so now we know the sensible load. Okay, how to calculate the sensible load? That is by means of losses. Okay, how much losses, right? Okay, then based on the losses, you can able to calculate the flow rate, right? And you should know what is the delta T, okay? What is the temperature difference, okay? Now for that, if I go to ASHRAE standard, okay, so this is the ASHRAE standard for the power plants, okay, chapter 28, right? I think you remember we have seen for the generator as well, right? So if you go to chapter 28 in the ASHRAE handbook, okay, you will find there is a table called table 1, design criteria for fuel to fire power plant, okay. Basically you have many equipments in the building area, right? So if you go to transformer, say for example you have a transformer, enclosed transformer equipment areas, right? Okay, so here what is the temperature? This is outdoor temperature. Say for example for the enclosed transformer 0.4 percentage slash 99.6 percentage. What is that meaning? Say for example if you go to ASHRAE guideline, right? If you go to ASHRAE guideline, say for example Dubai location, you can go to 0.4 percentage. What is that 0.4 percentage? It is the maximum temperature during that hour. Say for example in every hour or every year we have a total 8760 hours. Okay, so if you talk about maximum like 0.4 percentage, the maximum temperature will be approximate 43.3 degrees Celsius. Okay, so if you go to extreme condition, this will be maximum like 8760 hours. Okay, so this is the maximum temperature. Okay, then if you go to like last 10 years, what is the maximum? Last 20 years, what is the extreme maximum? Last 20 years, 50 years, what is the maximum? That is also method, because some consultant like critical consultant like hospital data centers, they consider like normally 20 years or 50 years. Okay, and but if you go to normal building services, okay, as per the standard, they say like they take 0.4 percentage for the extreme annual condition. Okay, so that is nothing but 43.3 degrees Celsius. Okay, then if you go to the ASHRAE guideline, they are saying about 99.6 percentage. That is during the winter. Okay, so if you go to the winter, you have a 99.6 percentage. The maximum temperature will be 13.8 degrees Celsius. So this is the maximum temperature, right, in the ambient. Okay, so this is the outside temperature. Now what is the maximum temperature you can go for the transformer as per the local as per the ASHRAE standard? You can go up to plus 6 degrees Celsius. So that means whatever the temperature as per ASHRAE plus 6 degrees Celsius. Okay, so this is as per ASHRAE condition. Okay, but if you go to local regulations, okay, local means like in our UAE region, if you go to here, this is the regulations from DEWA. Okay, here what they are saying, the temperature maximum will be 7 degree Kelvin, right? The maximum, the temperature difference. So if you go to our standard local guideline, the normal outside temperature will be 46 degrees Celsius. Okay, and how much maximum it can go? Plus 7 degree. So 46 plus 7, or the value is given in the DEWA guideline as well, 48 degrees Celsius. If you go to Safar, 46, but if you go to DEWA, they are considering 48 degrees Celsius. So what is the temperature difference? Maximum 7. So that means 48 plus 7 degree Kelvin. Okay, so this is the temperature difference. So we know the temperature difference and we know the heat losses, right, from the transformer. If you go to the catalog transformer, you can able to find what is the heat losses in the transformer from the like a core losses or winding losses. Based on that, you can able to calculate. Okay, now if you go to one of the equation, okay, which we have prepared for the transformer ventilation. Okay, so here what is that value? Heat dissipation. You can also calculate by means of transformer efficiency. Just now I said whether it is based on the losses. The loss is nothing but efficiency, right? How much efficiency? So if you go to this particular equation, heat dissipation, you have to calculate in kilowatt, right? Because normally in our equation, which is nothing but BTU per hour is equal to CFM multiplied by delta T multiplied by 1.08. But normally if you go to the transformer rating, it will be in kVA. Okay, like 500 kVA or 1000 kVA or 1250 kVA, 1500 kVA, depends upon your electrical requirements for that particular building. Okay, so how you calculate the heat dissipation? The transformer kVA rating. Say for example, I have a 500 kVA or 1000 kVA. Okay, now to convert into kilowatt, what you will do? You will convert from power factor, right? Normally in our local regulation, the power factor will be normally 0.8 or 0.9. Okay, it depends upon the local regulations. Okay, so when you convert from kVA to kilowatt, you have to multiply by power factor. Then it will be converted into kilowatt. depends upon the local power factor. So transformer KVA rating multiplied by power factor will give you kilowatt. Then multiply by number of transformer. Say for example, if you go to one transformer, one of the transformer room, you may have a multiple transformers, right? Say for example, this is my transformer room. So say for example, I have I will be having one transformer here. Okay, then I will be having another transformer here, right? So this number of transformers depends upon the required load based on the building. So based on that we calculate, right? Then if you go to this equation, you have a transformer efficiency. So how much efficiency the transformer, the balance will be the losses. So we are going to calculate the losses 1 minus transformer efficiency. So this transformer efficiency is based on what? Based on the core losses and winding losses. Okay. So say for example, if I enter 98.4 efficiency, this is based on the transformer. If I know that the transformer will produce only 97%, then you can enter 97.97, right?
This one will be given by the electrical design team.
Yeah, electrical designer, and also you can go to the catalog of the transformer. Sometime you will find directly the heat dissipation, same like generator. Last week we have seen how much heat dissipation in BTU per minute, or you will find how much efficiency, okay, for the transformer. So like a 97% or 98%. So the balance we can take, that will be the losses. So now to calculate heat dissipation, transformer kilowatt KVA rating multiplied by number of transformer multiplied by power factor multiplied by 1 minus transformer efficiency. That will give you the total heat dissipation in kilowatt, right? Okay, now what is our equation? BTU per hour is nothing but CFM multiplied by delta T multiplied by 1.08. Okay, so what is that BTU per hour? Whatever the heat dissipation in kilowatt multiplied by or divide by 3.516, you will get tonnage. Then multiply by 12,000, you will get BTU per hour. Okay, so we know what is the heat dissipation. And what we have to calculate? We have to calculate transformer ventilation. Transformer ventilation is nothing but the fan, right? So we are going to calculate the CFM. And what is the delta T? The delta T will be the maximum temperature, which is 48 degrees Celsius ambient, and plus, as per ASHRAE 6 degree, but as per local guideline 7 degree.
7.
Yeah, so this is the temperature difference. So that temperature difference you can enter here. So what is that? 48 degrees Celsius, right? So 48 degrees Celsius, you are going to convert into Fahrenheit, because this equation is in Fahrenheit. The delta T is in Fahrenheit. If you go to the equation table, so we have to convert into Fahrenheit. So 48 degree multiplied by 9 by 5 plus 32 will give you what is the ambient temperature. And for the maximum temperature, 55 multiplied by 9 by 5 plus 32 will convert into Fahrenheit. So what is the temperature difference? 13 degree Fahrenheit. Okay, now we know the heat dissipation, we know the delta T, and we know the other value, which is the factor, which is 1.08. So now you can calculate the fan capacity, right? Clear, right? The fan capacity in CFM. So if you want to convert into meter cube per hour, if you want to convert into liter per second, we can, by using the equation, we can convert. Clear? So now we calculate the fan capacity. Okay, say for example, if you go to this particular equation, okay, yeah, this local regulation, if you go, okay, so this is the transformer room, okay, or if you go to this particular one, in this layout, this is the transformer room, right? So in the transformer, you are going to provide, say for example, intake and exhaust, because if it is located in the basement, then you will not be having any fresh air from the louver, right? You cannot have, it's enclosed room. So if you go to the standard, also given forced ventilation for transformer at the basement, right? So that means it is enclosed room. So you have to provide one makeup and one exhaust. Okay, so whatever you are providing the makeup, that will take out all the unwanted heat, then it will be taken out by means of exhaust fan. So you can have a makeup air fan also the same capacity, and fresh air also having the same capacity. Okay, and say for example, if you want to go with sorry, there is a disturbance. Sorry. See, if you want to go with the ground level, then maybe you can go with the louver, right? Maybe you might have seen some of the project. They go with the louvers, right? If you go to any of the buildings, right, like the construction projects, if you go to the external area, you will find the louver. So that louver will be somewhat like this, right? So this louver, we have to calculate the free area of the louver based on the CFM, what we calculated. So we have to make sure that this particular pressure drop is considered in the fan. Whenever you have a fan here, that pressure drop is considered. Okay, say for example, if I have a 50 pascal, then I have a ducting, whatever the pressure drop should be calculated, then you have to consider in the fan calculation. Okay, and also if you go to the chart, okay, it is very simple to calculate the CFM. Okay, remember we have an equation here, right? We are calculating by means of this equation, we are going to calculate what is the flow rate. But if you go to the local guide, they also given one chart here. So this chart based on the losses, right? Say for example, if you go to this table, total losses, say for example, I have a 12.9 kilowatt, okay, multiplied by 4 numbers of transformer, which is 51.6 kilowatt. So this is the 51.6 kilowatt is the losses, okay. And what is the temperature difference as per the local standard? 7 degree Kelvin, right? So if you go to this particular chart, if you go to the line, you will get delta T 7. Okay. So if you go down, you will get the flow rate here in meter cube per hour, right? So this is also one method, direct method. Based on the losses, based on the temperature difference, you can calculate the total flow directly from the chart. Or by using the equation, you can able to calculate the flow rate. There are two methods available. Okay, clear, right? Does anyone have doubt for the transformer ventilation?
Clear. Parani, this calculation is in that folder, right?
Yeah, it is there in the folder. Yes, yes.